So rotational motion, what happens, only the angle changing, not x changing. So this thing is rotating in one place, the fixed axis. So we will be looking at how the angle is changing with time. So we will have something called angular velocity and angular acceleration, different from the normal velocity and normal acceleration. Could you please stop chattering? Then we went to look at what happened when the angular acceleration is constant. So we said we can use similar equation like we have for chapter 2. When the acceleration is constant, we can use these equations of kinematics, and we will have a similar equation for rotational motion. All that happens, x become replaced by theta. Could you please put your phones away and pay attention to me? Excuse me. And v will be replaced by omega, and a will be replaced by alpha. And the same idea, we even did a question. Then we talked about, what about the linear speed? When something is moving, it will also have some linear speed. We call it tangential speed. Then we showed that this linear speed is related to the angular velocity, angular speed, angular velocity, by this equation. And similar equation for acceleration as well. The tangential acceleration and the angular accelerations are related by chapter 7. Chapter 7. Yeah, we still have some left, okay? So I'm just going through what we did before quickly. And then we talked about centripetal acceleration. That is when, when something going in a circle or a curve, and it will have an acceleration to the center of the circle due to the changing the direction of the velocity. It is called the centripetal acceleration. And we can prove it, but we did not actually prove it. The direction of that acceleration is toward the center of the circle as it's moving around. And the magnitude of the acceleration, the centripetal acceleration, is given by this equation. You just have to take that as it is. We don't need to worry about how to prove that. And we can also express this in terms of the angular velocity instead of the this linear speed. So in terms of angular speed, r omega square, both are correct. Suppose we only know the omega, we can use this equation. If you know the speed, we can use this equation, the linear speed. Right, then we told you that, if the alpha is not 0, if something is moving with the increasing angular velocity, so alpha will not be 0, then there will be an angular acceleration, and with that we will have a tangential acceleration as well. So in general, an object that is moving in a circular motion can have tangential acceleration, which is like that, the red arrow, and centripetal acceleration because of the changing in the direction of the velocity. So the total acceleration will be the sum of these two acceleration. And then we said, since these two accelerations are perpendicular to each other, the magnitude of the total acceleration can be given as the square root of the sum of the squares of the two accelerations. Right, that is where we stopped. Now we come to the dynamics of circular motion. That is, in other words, we are going to apply the Newton's second law, which is this: net force is equal to mass into acceleration for circular motion. So it is the net force, and the force will be directed, because acceleration is directed to the center. The direction of the force will be, we must have a centripetal force. We call it as a centripetal force because it is directed toward the center. So the net force in the radial direction along the direction of the centripetal acceleration is equal to mass multiplied by the acceleration. Now we know the acceleration is the centripetal acceleration. So this is the net force in the direction of the centripetal acceleration. We also denote it like that. The C stands for centripetal. So instead of putting it like this, some of all the forces that is directed to the center, we can also just say FC. So F sub C simply mean it stands for the net force in the direction to the center of the circle. So we call it a centripetal force, the forces that is necessary to keep something moving in a circle. So provide this centripetal acceleration. So we know this can be written like this in terms of its speed and the radius of the circle it is describing. Right. The examples are for centripetal force. If you take a string or a rope and tie something to the end of that and make it go in a circle, it can be a horizontal circle or vertical circle or some other direction. The centripetal force will be provided by the tension in the string. So that is one. Gravity force can also be a centripetal force. We know the planets go around the sun, almost a circular path. So what is the centripetal force there? The gravitational pull of the sun pulling those planets to itself. So it needs, because it's going in a circle, it needs a force toward the sun, which is at the center of that circle. So actually it is not a circle, an ellipse, but it doesn't matter. Let's assume it's a circle. The same thing goes for elliptical orbit as well. So the gravitational force is another example of centripetal force, which makes all the planet to go around the sun. Friction force also can be a centripetal force. It's like when we have a car, or we will come to that example in the next slide. So let's look at this one. The tension in the string. You take a string or a rope, tie it to a disc, and let it rotate in a flat horizontal table. And as this is rotating, say it's going clockwise, it is describing a circular path. That means there is an acceleration to the center of the circle. Somebody must provide the force necessary to have an acceleration to the center of the circle from the Newton's second law. If there is an acceleration, it must be due to a force in that direction. Without a force, you cannot have an acceleration. So the force is provided by the tension in the string. You can see it is also directed toward the center of the circle, applied on that disk. So here is an example of the tension providing the centripetal force. We are going back to the equation again. So the centripetal force, which can be coming from many forces, this Fc stands for the sum of all the forces in the direction toward the center of the circle, equal to mass multiplied by the centripetal acceleration. So for centripetal acceleration, you can substitute speed squared divided by the radius of the circle. Now, what will happen if you don't have a force? For example, in the direction of the acceleration, we can do that. Say we make it rotate, and suppose you cut this string, the tension will vanish, right? If someone cut the string, there will be no tension. So there is no force to keep this guy going in a circle, because you cut the string, the tension is no more. So what will happen to this disk? This will fly off, right? It will just continue with the same velocity it happened to have at that moment. So it will go like that. So it will not describe a circle anymore. The moment you cut the string, the tension disappears. So it has no force to keep that going in a circle. So this disk will fly off tangentially to that circular path. So that tells you, if something has to go in a circle, it requires a centripetal force, which is also toward the center of the circle. So the moment it disappears, it cannot go in a circle. It will just fly off with the whatever velocity it has. It will continue with the same velocity, because there is no force to make it go in the circle. Right. The name centripetal force is just a classification. that include all the forces acting toward the central point of the circle. By itself, it's not a force in itself. So centrifugal force must be supplied by some actual physical force. Now we are ready to do a question with whatever we learned. The question example problem is this: a race car, accelerates from starting speed of 40 meter per second to 60 meter per second in 5 seconds while traveling in a circular path. Okay, so the car is here, say at one point, it has a velocity of v1 equal to 40 meter per second. Then it reaches this point, let's say now it has the different speed, say v2 is equal to 60 meter per second, and the time it takes to go from here to here is 5 second time elapsed. So this is the data given to us. The car is describing a circular motion. Okay, it is not going in a straight line path, but in a circular path. And the radius of this circle is given 400 meters. So question A is asking, when the car has this speed, it must be between this, right? Here it has a speed of 50, here it has a speed of 60. So somewhere in the middle, maybe let me call it V3, it has a speed of 50 meter per second. So when the car is somewhere here in the midway between these 2 points, we say it has a speed of 50 meter per second. At that point, calculate the magnitude of the centripetal acceleration that car has. That's a straightforward question. The centripetal acceleration is given by this equation. It's equal to speed squared divided by the radius. The speed is given, substitute 50. The radius of the circle is given, substitute. Just putting in your calculator, work it out, you will get this answer, 6.25 meter per second square. Done. All right. Okay, now, next question. What is the angular speed when it is at this point? The tangential speed is given. This is the tangential speed, right? It has a speed like that. V3, I call it 50 meter per second. So if you know the tangential speed, you can find the angular speed. This is the equation. Vt is equal to r omega. So omega is equal to Vt divided by r. You just substitute Vt is equal to 50 and r is equal to 400. You get that. So B is also done. Straightforward question. The tangential speed is given. Then you are asked to find the angular velocity. That's the equation. You apply it and you get the answer. C. What is the tangential acceleration? Okay, now this is a bit tricky because you're asking what is the tangential acceleration at this particular point, right? And we have information to find the average acceleration from here to here because the initial velocity is given, final velocity, well, the magnitude average acceleration, if we make it very small duration, well, 5 seconds, we have the initial velocity and the final velocity. Then you can say the average acceleration by the definition of average acceleration, delta V divided by delta T. Delta V means the velocity at the end minus the velocity at the beginning. So V final minus V initial divided by the time. That will give V the average acceleration while this car is moving from here to here. And we will take that average acceleration to be the acceleration at the midpoint. Okay. It's not very accurate, but from whatever the information we have, that's the only thing we can do. We just find the average acceleration and then we equate it to the acceleration at the midpoint. It will be, since it is going with a constant speed, okay, it is not going, it's going steadily increasing speed. So we are going to assume it's a constant acceleration. We can prove that the average acceleration is equal to the acceleration at the midpoint. So that is fine. D. What is the magnitude of the total acceleration? So we have this equation for the total acceleration, which is square root of the sum of the squares of tangential and the centripetal acceleration. We found centripetal acceleration in A, take that value, and we found the tangential acceleration in C, take that value, substitute, and we find the total acceleration. Okay, right. So that is done. We can move on to give more application of this centripetal acceleration and the centripetal forces. There are very interesting specific situations where we will be using this knowledge. In a level curves, what do you mean by level? What do you understand? Level mean flat, okay? So when a vehicle on a road, a level road, so if it is making a circular path, maybe in a turnus, a curve, okay? Maybe there's a curve on the road, so you can say this car is describing a circular motion of certain radius r, the curvature, radius of curvature of this particular curve. So that is one example where we're going to apply our knowledge of centripetal forces and centripetal acceleration. Then comes curve again, but banked curve. What do you mean by bank? If you are driving in the highway, okay, probably you notice the road is not level. Especially when you have a curve on a highway, the road is not flat. The road is banked, right? It tilted like that. So that is what we mean by banked curve. So I'm just introducing now, then we will go one by one, each of them. So why do we bank the road? So we will explain using our knowledge now, what we learned about the centripetal force and the centripetal acceleration. Horizontal circle, well, I can give an example of horizontal circles where practical day-to-day life example is a merry-go-round. Have you heard this word, merry-go-round? In amusement centers, in this, we have a disc, a horizontal platform where children get in because very light, not dangerous. Children can get in, and the thing goes round and round. Maybe there will be chairs, they'll sit on this. That's merry-go-round, a horizontal platform. So that is an example where we can apply our knowledge. Vertical circle, roller coasters. Right? This is an adults, children are not allowed, where the thing goes up like that vertically. That is roller coasters. So we will take these examples one by one and see how we can apply these centripetal force that we learned. So here we are looking at a car which is, excuse me, come to the front, please. Please come to the front. Yeah, now, yeah, please. So this car is on a level road. Okay, now what we are looking at is the back of the car. Let's say, imagine this is what I'm holding is the car. It is going in a curve. Okay, now you are looking at this point. You are looking at the back of the car. So it's on a flat road, level road. It is going like this. So it is describing a circular motion. Momentarily, at that moment, it is not going on a straight road, but in a curved bend road. Right. So if that is the case, it is having an acceleration to the left like this, right? Centripetal acceleration. So if this is the curve, so there must be a centripetal acceleration because it's describing a circle. So the direction of the centripetal acceleration will be toward the center of the circle. Center of the circle is somewhere here, right? Is that clear? Right. Yeah. You mean in an actual question, you mean? We will make it clear from the picture. I mean, maybe you have to read the question to understand it. Okay, well, here I am describing it, now you understood, right? So similarly, in the question, there will be some description. You have to read the text and understand. If it is not clear from the figure, you need to read the question and understand. Yeah. Don't ask any, don't distract me, please, at the end. Don't do that. Focus on the course, please. Okay? Right. I will answer you at the end. Now, so this car is going in a circle, and the radius, center of the circle is here. So the direction of the acceleration will be like that. Right. Now, there are not much text here, but I am explaining it, so you cannot complain. I have made you understand, right? Okay. Now, if there is an acceleration to the left, because that is the centripetal acceleration direction, you cannot have it unless there is a force in this direction. Newton's second law. An acceleration is possible in a certain direction only if there is a force in that direction. Okay. Now, what are the forces acting on this car? It has a weight, mg, like that, and the normal force that is from the road on the tires. Okay. So there is a normal force and the gravitational force. Let's say these are the only forces, okay? On the face of it, it looks like those are the only forces. Now, if these are the only forces, how can we don't have a force in this direction? These have no component in this direction. What is this angle? 90 degrees. So cosine 90 is 0. So the normal force cannot contribute to the centripetal force because it has 0 component. It's like the xy axis. If a force is in the y-axis, it cannot do anything in the x-axis. So this is the y-axis, this is the x-axis. So this force has no contribution in the along the centripetal acceleration direction. So normal force cannot help. It cannot be the centripetal force. What about mg? It is also 90 degrees. It also has 0 component. That means this car cannot do this bend because none of these two forces going to help or give the necessary centripetal force. But you know the cars can go in a circle. It is possible. We make turn. There must be a force there. You know what that force is? Friction force. Okay. So the friction between the tires of the car and the road, there's the static friction. So it's already shown here. So that is the force which is the centripetal force. So this is why, suppose there is no friction, suppose ice. Let's say the road is ice. You know, ice has 0 friction, almost, right? It's not exactly 0. So if the guy tried to make the curve, will he be able to do it? No, it will be just flying because the friction is 0 almost or not enough. So especially if he's coming with a big velocity, he will just go forward. He will not be able to move. The car the tires he may be able to turn the tire, but with the tire like that, he will go forward. He will slide in the snow or the ice. He will not be able to make the turn. So now you understand how we can apply our knowledge. So what happens, the centripetal force must be of this magnitude, right? Because mass multiplied by the acceleration. So if you know the radius of this circle that you are trying to make, if the radius is big, okay, the force will be small, right? Radius is in the denominator. Big radius means the curve is not very sharp. The car will be, the force is not that great. But small, sharp curve mean then you need a big force. Similarly with the speed. If the speed is big, you need it's a big force we needed because the acceleration become big. If the speed is small, maybe you'll be able to make the curve if the force is not that great. So this is why when you try to take the curve, if there is on a level flat road, if you are making a curve, you should look at how much friction you have between the tire and the road. Okay, so otherwise we'll be in trouble. So we can actually get an expression for the maximum speed we can have that allow us to take this curve with the radius of curvature of this much, and this is the coefficient of friction between the tires and the road, μs. We can get this equation. Okay? You're not supposed to memorize this, you're supposed to derive it from the Newton's second law. Let's do that. So this is the Newton's second law. Net force in the acceleration direction is equal to mass multiplied by the acceleration, the centripetal acceleration. So we'll substitute now. So the only force, this guy cannot help. This guy cannot help because this is the direction. So only the friction can help. So let's say it is reached a value where we want to find the maximum speed that car can go and take this curve. So that means we have reached the maximum force available. The static friction force has a maximum value. So I will use that value. Fs max is equal to m and acceleration, centripetal acceleration, v squared over r. And then we know something from your chapter 5. The Fs maximum, the maximum value of the static friction force, is proportional to the n multiplied by the proportionality constant, which is called the coefficient of static friction. So instead of Fs max, I can write mu as n and m v squared over r. So we come there. Then we look at this n and look at the car's free body diagram again. So you can see that in the vertical direction, the car is not moving up or down, right? It is only moving horizontally. It is not moving vertically. So I can say the forces must be balanced because there's no acceleration in the vertical direction. N must be equal to mg. So I substitute that n is equal to mg. Then you get this equation. Now you see the m cancel with m. Then you arrive at this expression. So I'm going from there to here. Then I do some rearrangement, bring the r here. So you get this. Then take the square root both sides, you get this. So if the coefficient of friction is given for that particular road, and if you want to make a say, suppose the car has to go at a maximum speed of say 100 kilometers per hour and take that turn, then you have to make sure we have this much of friction between the tires and the road. Otherwise, it will not make that curve. So this is one of the application of what we learned using the centripetal acceleration and the centripetal force we just learned. Okay, now we go to this. What's the difference now? The road is banked. Because in a highways, the cars has to go fast, like 200 kilometers per hour if it is allowed. So if you need to take a curve, a bend, you have to make sure there is enough centripetal force for this car to do that curve. Otherwise, what will happen? The car will be skidding, right? It will be, if it is a flat road, and let's say you are going at a speed of v is equal to, say, 200 kilometers per hour, and the friction force, even the maximum value, will not be enough to provide that mv squared over r, because the speed is so huge. So the car will skid. It will fly away, right, from that circular path. It will be just keep going in whatever direction the velocity it has. So this is why we do a trick. The trick is, instead of keeping the road level, we make the road banked, set at a certain angle of theta. Tell me what happens now by doing this. If it is a level road, this n cannot help, because making a 90 degrees. This is making a 90 degrees. mg also cannot be, let's say this road has no friction. Let's forget about the friction. Let's say the friction is very small because this is a very big speed. Friction cannot help. So let's assume there is no friction. We do a trick. The trick is You bank the road. When you bank the road, what is the direction of the normal force? Is it vertical? No, because the normal force will be perpendicular to the surface. The surface is now like this, so the normal force is not vertical, it is like this. And if the banking angle of the road is theta, the normal force will make an angle of theta with the vertical. So now this force has a component in the needed direction. The component of this force will be n sine theta. The component of you guys come late and you are doing something else. The four of you are trying to talk to each other as well. So why are you whispering to each other? I hear you. Come on. I don't know which one of you there is talking. So now the n sine theta is not zero anymore because theta is not zero. Okay. When it is completely vertical, theta is zero. Then the n sine theta will be zero. It is useless. But the moment you incline the road, bank the road, then it is possible for this normal force to provide the centripetal force. So now if someone asks you, why do we bank the road? You have an answer. What is the answer? To provide the centripetal force from the normal force. If it is level road, can the normal force provide the centripetal force? No, because n sine zero, because theta is zero when it is vertical, so n cannot help. But the moment you do like that, the normal force can provide the centripetal force by an amount of n sine theta, and it is not zero. We are okay. Even if there is no friction to help, if say suppose the friction is small, we can get a big help from this normal force. So that is the reason. mg cannot still help because mg is still 90 degrees. mg cannot help. It's only the normal force which can help. How can mg help? The direction, centripetal force direction must be this. This is the direction of the, because still it is making a horizontal circular path. But if suppose this is the road, it's like this, it is going like that. Okay. Hand is not moving, only the car is moving, but I need to move the whole hand. So the car is going like that. So the circular path is like that. So centripetal acceleration direction will be here. The center of the circle is here. What about mg? Can mg help? No. mg is making a 90 degrees. The direction mg is still vertical. Only the direction of n is an angle to the vertical. So the force is n sine theta. Now I can again apply our Newton's second law. The net force in the radial direction toward the center of the circle is equal to mass multiplied by centripetal acceleration. So the only force, because we are ignoring the friction now, that can give the support is the normal force. Its component is n sine theta is equal to mass multiplied by centripetal acceleration, right? Now, what about n here? Can I say n is equal to mg now? No, that is wrong. Because look here, so this is a free body diagram. You have the n like this, but its x component is n sine theta, because this is the angle theta, and the y component is n cosine theta. So if you apply the Newton's second law in the vertical direction, it is not n which is balancing with mg, it is n cosine theta which is balancing with the mg, and the acceleration is zero, so you get this. When you apply the Newton's second law in the y direction, net force in the y direction or the vertical direction equal to mass into acceleration in the y direction. There is no acceleration in the y direction because the car is only moving horizontally. It is not going up or down, say steadily in the same level. So there is no acceleration in the y direction. So you get n cosine theta minus mg is equal to 0, which gives us this. So n is equal to not mg, but mg divided by cosine theta. Now I can take that expression and substitute here. So then instead of n, you get this, and sine theta, and mass into acceleration, m cancel with m, you get this small expression here for the centripetal acceleration for a car moving, a vehicle moving on a banked road with the banking angle of the road is theta. The centripetal acceleration is g tan theta. Now I can further reduce this expression by substituting AC is equal to v squared over r. That will give me, so this is v squared over r, and you can bring the g to this side. So tan theta is equal to v squared divided by rg. So as an engineer, say civil engineer who is want to construct a highway road and you want to take a turn, then you can use this angle, this equation to determine what should be the banking angle. So if you want to have a highway which can accommodate a car going at the speed of say up to 250 kilometers per hour, you substitute that speed here and you get the radius of curvature of your bend and substitute for g, then you can calculate the necessary theta for the banking of that road. Okay, this is another application, an interesting one. It's even more interesting. It's a roller coaster ride, right? So this is not a horizontal circle, but a vertical circle. So let's see, this is the roller coaster vehicle. When it is at the bottom here, you can apply the Newton's second law, which is this. The net force to the center of the circle is equal to mass multiplied by the centripetal acceleration. So the normal force, the direction of this acceleration is upward. So let's take that as a positive direction. So the normal force is also positive, it's also upward. And the gravitational force is downward. So negative mg or minus mg equal to mass multiplied by, this is the expression for the centripetal acceleration, speed of the roller coaster vehicle at the bottom, divided by the radius of the circle that roller coaster structure has. So, well, you can now, move this to the other side. Maybe suppose someone asks you, calculate the normal force. Well, this is the equation. Am I going to give this equation in the formula sheet? No. All you need is in the formula sheet is this, Newton's second law. So then, depending on the situation, the question, you should be able to derive this, whatever the equation you need, starting from the Newton's second law. Show the forces and so on, and you get this expression. Okay, now what about when the car is at the top? That is really more interesting. Let me show that. So now it is going to be a different equation. When the roller coaster vehicle come to the top here, what is the direction of the normal force? Because this is the truck, this is the track, okay, and let's say my hand is the track and the roller coaster vehicle is coming up, because it is upside down. So the roller coaster must be pushing on the track, right? So that means normal force will be down, because the vehicle must be touching the track and the track must be pushing the roller coaster vehicle down. So the direction of the normal force is down. So you see here, the red arrow, it is down. Mg is also down. Both of them are down when it's at the top of the track. So you apply the Newton's second law in the direction of the acceleration. What is the direction of acceleration? It's also down. So let's choose the direction of acceleration of a positive direction. Down is the positive direction. Therefore, n is down. Therefore, it is positive. Mg is also down. Therefore, it is positive. In the other side, mass multiplied by the centripetal acceleration, which is positive, is down. So the speed there squared divided by the radius of the circle. So this is what you have when the roller coaster is at the top. Okay. Now let me rewrite this equation this way. Get an expression for the normal force. It will be m v squared over r minus mg. Now you can see what's happening here. If this mv square, the centripetal force, is greater than mg, n will be positive. If this mv squared over r is greater than the weight mg, n will be positive. That means the roller coaster vehicle is touching the track. It's not falling. It is still in contact with the track. So that tells us this value must be at least equal to mg. If it becomes less than mg, that means you are falling. The vehicle will drop because it's not touching, right? N has to be at least 0. It's about to fall, but it's still touching, not touching. Okay, so it is just about to fall. So the critical value is, we will say this equal to this, and then get the speed. So when you cancel this, so then v squared is equal, v squared over r is equal to g. That means v squared will be equal to r multiplied by g. Then if I take the square root both sides, v equal to square root of gr. So this is the speed, the minimum speed it should have when it is at the top. If the speed is less than this, then this becomes negative. That means you are not touching. N negative mean there is no contact between the roller coaster vehicle and the track. So now this is another application. So as an engineer, suppose you want to design a roller coaster ride like this with a certain radius, let's say, say 50 meters or something. Then you have to make sure when the roller coaster is coming here, the speed must be at least this value, g into r. So g is 9.8, and you say so you want to design something is 50 meters, so multiply by 50 meters. So you have to calculate this and make sure you must have enough speed here. So when it comes to the top, its speed is greater than whatever you get for square root of gr. If not, disaster, you will fall. Actually, we can do this at home, this experiment, like this. Now we know the speed is gr, right? The minimum speed that should have is gr. So you take a bucket, fill it with water. It doesn't depend on the mass. It only depends on the radius of the circle vertical circle that you are describing, and the g. G is a constant, 9.8. So you can say, if you take a bucket and you fill it with water, you go like that. What is the radius of that circle? Maybe 1 meter, maybe less than 1 meter. Let me take it easy for me too. Let's say it's 1 meter. G is 9.8. So somebody tell me how much it is? 3.1 something. Okay. Square root of 3.1 meter per second. Right. When you say meter per second, you don't have an idea how fast it is. But if I give it in kilometer per hour, you will know. So convert to kilometer per hour, multiply by 3.6. Somebody tell me. It is something like 11 kilometers per hour. Yeah. Multiply by 3.6 will turn the meter per second into kilometers per hour. It is about 11. It's not a big speed, right? You're driving the car 11 kilometers per hour. It's a very small speed. You can achieve it just with your hand. You take a bucket filled with water and you go like this. But you cannot stop there. You have to keep going with the same speed. Make sure the speed is at least 11 kilometers per hour. You will make it. The water will not come out of the bucket. Right. So this is the last slide. Then we will take attendance. Then we will do some questions. When you go in this, even the roller coaster ride, you feel you are being pushed away from the circular path, right? And people call it as centrifugal force. But that's not actually a force. What is happening here is the centripetal force that is needed is not enough. So you cannot stay in the circle, you'll be pushed out. You will try to escape from that circular path. So you will try to go because of inertia. This is just an effect of inertia. You will go tangential to that circular path. It will feel like you are pressing, you are pushed away. But it's not really, there is no pushing, there is no such force. So we call it as fictitious force. Okay, it's not a real force, a fictitious force. What is this fictitious force? Is actually the absence of enough centripetal force. So you cannot be held in that circle, so you will be pushed out, and it feels like some force. It's not an actual force. So this question, you have to convert the 2 pi over 3 radian into revolution. So you need to convert the radian to rev. Why did I put the radian down, not up? So that I can get it cancelled, right? So one revolution is 2 pi radian. Simple as that, right? So that done. So you see the 2 pi cancel with 2 pi. So it is equal to 1 over 3 revolution. 1/3 of a revolution. It's already there, right? And none of the other answers have 1 over 3. So you don't have to even do the second one. But anyway, for practice, we'll do the second one as well. The second one is to convert the 2 pi over 3 radian to degrees. So the conversion factor will be radian should go away. So since it's up, I have to put it down. And up, you should have the degree. Now you know the conversion. You can say 180 degrees or 360 degrees, if you can't remember, is equal to 2 pi radian. That's it. You cancel this with this, and 360 divided by 3 will be 120. So, okay. Easy, right? So this is, I mean, if you look at the midterm 3, even every midterm exam, I repeat the question, the same question. Basically the same question, sometimes exactly the same question. So you will have a question like this coming again in the Thursday exam. So, once it's like I'm telling you what the question going to come. I don't think other courses you get to see the midterm exam papers. Here you get to see the formula sheet is given, midterm exam papers are posted. You should get full marks. Okay, right, let's. Question number 15. If a wheel turning at a constant rate complete 15 revolution per minute, RPM, right? That is called RPM, revolutions per minute. So this is the angular velocity, but you're asked to convert this to radian per second. It's a chapter 1 question, conversion of unit. So you go one at a time. So you will attack the revolution first. Yeah, you convert the revolution to, because revolution is up, you better take the revolution down, right? And it's the corresponding to the radian, right? So the conversion, one revolution is 2 pi radian. So you got the revolution out of the way. Now it is radian per minute, not good enough. The minute has to be converted to second. So you need to have another conversion factor to get to the minute. Minute is down, so you should have the minute up here. And second. Now, so 1 minute is 60 seconds. That's it. Then you just take a calculator. You see that minute also gone out. What is left is radian and second. So all the numbers, collect them. 15, 2 pi, anything else? No. Down only 60. The 1, you don't have to write the 1. So take your calculator, work this out. You will get 1.6. That's it. All right. So, you are just in chapter 1, it's not something new, right? It's something we already learned and hopefully mastered it. So you don't have to study anything new, but you have to practice, okay? In exam situation, you're under stress and sometimes you go blank. That's why you need to practice a lot of questions, then you feel confident, you don't lose control. Number 16. When you ride a bicycle on a straight road, in what direction is the angular velocity of the wheel? Left. Yeah, thank you. So say this is a bicycle. I'll explain to other people who doesn't know how. So this is the wheels of the bicycle, and you're here sitting in the bicycle, and let's say you're going like that. And if you are moving forward, which direction the wheel turning? This way or this way? Front, right? Okay. So that is the first thing to understand. The wheel is going like that. So the wheel is pushing on the floor to the backward. So the floor will push the wheel forward. So we'll move forward. Right. Now, what is the direction of the vector, velocity vector, angular velocity? Take your right hand. Don't use the left hand. Okay, everything will be opposite. Take the right hand and hold it such that you can turn the fingers without the thumb in the direction of rotation. If I keep like this, you're turning like this, right? No, wrong. So you have to turn it like this. Then look at the thumb. Thumb is pointing to the rider's left. So you are the rider. You. So to your left. Okay. Okay. So it's a nice question. You will see that I repeat this question in different forms. You got it now? All right. Very good. So that is because the angular velocity has a direction, right? Angular velocity vector has a direction. You get it by rotating in the direction of that. And if it is, looking at this, if it is clockwise, is into the board. If it is counterclockwise, it is out of the board. Right, next one. Now this time, you need to understand this north, south, east, west. If someone asks you, what is the, show me the north direction, if you show like this, is it correct? Never correct. The north is horizontal direction, right? It's a north, is a horizontal direction. So this sheet I'm showing here, say this is a road or something, this is parallel to the earth. Okay, north, south, east, west are all horizontal direction. Let's imagine, say this is north. Suppose this is north. Then what is this direction? Excuse me. West? East. Please, you need to remember this. Maybe I will give the question without any figure. For what? In Arabic, Shimal, right? Shimal. Shimal is north. Yamin is south. Come on. I know you don't know. Right? Shimal is north. Yeah, well, let's use English, right? So north. If you are facing north, listen to me. If you are facing north, back is south. Opposite to north is south. Your right hand direction is okay. Please, man. No, it's always that is the order. If you are facing the north, your back direction is south. Opposite of north is south. Your right hand is east. Your left hand direction is west. You know now, right? I will not give a figure. You should know how to answer this question. You should be able to imagine this picture, visualize the picture. Right now, if the guy is going north, he's going south. Okay, the guy is going south. So he is going this way, south. And now his right hand will be east. And if you are going north, I'm sorry, I said this is the north, right? Now, if this is north, if I'm facing the south, my right hand will be west and the left hand will be east. Please don't make a mistake, right? Okay. Anyway, here you are helped. The directions are all given. And you can picture this, right? This is one plane. This is the road. And this guy is going south. And you can see already his right is west, his left is east, his back is north.
But the question will be like this. The picture, the figure.
I may not even give the figure. I'm telling. Right? So now you know how to master this, you know what is north. If this is north, where is the east, where is the west, where is the north? Yeah, but you need to know the content. I cannot pass you without knowing these things. The purpose of the exam is to make sure that you know how to do this. Uh, right, yeah. Let me continue. Yeah. Are you asking a question? Yeah. Yeah, I'm coming to that. I'm not done. Please pay attention. I'm just explaining so many things, but I didn't come to the question yet. What is he asking? Is he asking for angular velocity? That is already tested in the previous question. Now the question is not angular velocity, angular acceleration. Right. Now comes the complicated part. Okay. Now, I mean, not complicated. Once you understand, nothing is complicated. Now he is going south. And his angular velocity is, to his left, right? The left is to his left is east. You don't have to, you look at the figure. Okay. If the figure is not there, you better draw the figure yourself. Okay. So his left side, you can memorize. Your bicycle rider, when you go forward, angular velocity direction of the wheel is his left side. So left. So if the question is what is the direction of angular velocity, the answer is east. Okay. But is that not? It is not the question. The question is what is the direction of angular acceleration? Right. Now comes another thing you need to know. Right. If an elevator problem, remember the elevator problem, one-dimensional linear motion. If the elevator is going up, velocity is up. That is no problem. What about the acceleration? Now, if it's a constant velocity, zero. If the velocity is changing, it is not zero. It may be up, it may be down. It depends on whether the speed is increasing or decreasing. If the speed is increasing, it is the same as the velocity direction. If the speed is decreasing, it is opposite. It's the same thing here. You know the direction of the velocity is east. Okay. He's asking for the angular acceleration, because it is decreasing speed. So answer is west. Suppose I said increasing speed, the answer is same as the velocity direction is. Suppose I say he is moving with a constant speed. What is the direction of acceleration? Yeah, what is the direction? Yeah, value is zero. What is the direction? No, if it is zero, can you talk about direction? Yeah, yeah. The answer is no direction. I mean, if something is zero, how can it have a direction, right? So, okay, all right. Yeah. That is the right hand rule. If something is rotating like this, this wheel is rotating like this, right? You are going south, the wheel is rotating like this, so it is my left hand direction. If you are going south, my left is east. Yeah, left is east. Yeah. Always better to draw a sketch a figure, otherwise you